Okay, so let's get started going over this molecular model quiz given these two molecular structures. One is a polyatomic ion. It's very important you recognize that. But let's start with IF3. Now, what I'm going to do is I'm going to start with dots on a piece of paper, and I'm going to be able to answer all these different types of questions. Pretty amazing with dots on a piece of paper using valence electrons, which we eventually get from the Schrodinger equation, and we get to explain a lot of the known properties of these things just by starting with dots. So we're going to do that. So Lewis dot structures are just that, dots in a piece of paper. We're going to start with the valence electrons. Now, I'm going to rough this out first, and then I'm going to clean it up to make it make sense to me. Again, many different ways to show this correctly, but the final product is the one that's going to make sense and help me answer all the other questions that that are based upon this Lewis dot structure. So let's get started. Let's be crazy and start in order. So I'm going to start with iodine, okay? And good old iodine in the middle. And I know it has 7 valence electrons. It's a halogen. So I'm going to draw those. And I put out the valence electrons as dots. And I know there's 7. And I'm just going to write them this way. You know, and some people will teach that the top 2 that I'm writing right here are the S, and the others that go around here are the P. It doesn't really matter. But, so I've got 7 dots. Now I have 3 fluorines. Now I'm going to draw a fluorine as another color, but you don't have to do that. And so, what do we know about fluorine? Fluorine has 7 valence electrons. So it's kind of confusing. I say, well, wait a minute. Fluorine's bringing electrons to the table too. This has 7. How do I do this? Well, the way that I best think about this is take a fluorine. I know it has 7. So it has 1, 2, 3, 4, 5, 6. I'm going to take one of its 7 and pair it up with one of the iodines. Okay? And so if I think about it, I've got this fluorine right here bonding with just the 1 electron from the iodine. And then fluorine's definitely stable. Remember, fluorine's a row 2 element. So therefore, it is locked by the octet rule. It fills its S and its 3 p orbitals, and of course 8 is where it wants to be. Iodine, of course, is not a row 2 element. It's not an n equals 2 element. So it can have an expanded octet. Yeah, it can have more than 8. All right. Any case, let's add the other fluorines around so we can see. And so I'll add another fluorine here. And again, this is the rough way to do it. And then I'm going to clean this up to see if I can explain my structure, because you don't want your Lewis dot diagram to be such a mess that it can actually hinder you in trying to answer the other questions. Okay, so I've got 7, and I have 1, 2, 3, 4, 5, 6. I'm gonna put that 7th one here. And just by drawing a circle, and you don't need circles in your Lewis dot diagram, but it does help to see where it's sharing. And there's another fluorine there. Okay, and of course there's 3 in the molecular diagram. And so we're gonna draw another fluorine here. Okay. And of course it has 1, 2, 3, 4, 5, 6, and I'll put that 7th one here. And by drawing circles, I can see that this fluorine, okay, has its 8. All right. By taking 1 with the iodine. I know it feels strange. We haven't done it quite like this before, but it's really the only way to think about how you would do this. Now, iodine, okay, I'm going to show you that there is what? Oh, there's 2 lone pairs remaining and another 2 lone pairs. So what I just did here by taking 1 electron from the iodine and hooking up with the fluorine, who of course is going to be terminal because it just needs to have 1 unhybridized p to be filled here to make its octet. I notice I'm using 3 of the iodines to help stabilize the 3 fluorines, but then I have 4 left. And then I know that these lone pairs, we're just always going to put them into a single orbital. And so, yeah, now you can actually count, okay, count how many what? Filled orbitals we have. We have 1, 2, 3, 4, and 5 pairs of electrons, whether they're what? Non-bonding or in what? Bonds around the central atom. And so now I know in this hybridization, there is 5 domains. There are 5 areas of electrons that repel themselves into this shape. And so I can answer this question already. This is going to be an S mixing with a 3 P's because we have 5 of them. So this is what? 1 S and 3 P's. It's 4. And then I need a what? A D. So this is sp3d hybridization. Okay. Now, what I'm going to do is clean this up. Okay, I'm going to redraw this to make more sense. And I'll just do it over here, okay? Because I want to, again, I don't want to confuse myself on what this looks like. Now, what does it look like? Well, I know that 5 pairs of electrons, bonding or non-bonding, are going to make something called a trigonal bi-pyramidal family, okay? So let me help with that. I'm going to have an iodine in the middle, okay? That's my central atom. And there's something I know from this family, or something I should know, is that the lone pairs are always going to be in the equator position. So that tells me I'm going to have a fluorine, okay, we'll keep that as red, in the axial position. I'm going to have another fluorine in an axial position. And then I'm going to have another fluorine, or at least because there's only 2 axial positions in this shape. And then I'm going to put another fluorine in an equator position. Now I'm going to put the bonds here. Now when you put the bonds, make sure, again, you don't have to do dots. This would be acceptable for your Lewis dot diagram. A mess, and it could lead to these questions, okay, being wrong based upon, you know, the spatiality and the geometry of what they repel into. I'm going to put them into what they repel into. Any case, iodine's in the middle. Fluorine is going to have 3 lone pairs. You must draw these lone pairs. If you don't, your Lewis dot diagram is wrong. You must always draw the lone pairs. Okay, so the fluorine is going to have that. And then this one, of course, is going to have that. Remember, the dash in between the iodine and the fluorine represents a pair as well. Okay, and then, of course, I have the 2. I'm just going to draw a dash and put a pair here. Doesn't mean that this pair is bonding. It's an orbital with 2. And then I have another one here. And so what I'm trying to show is that if we remember, the bond angles within a filled trigonal bipyramidal are 120. So I'm trying to show this is 120, this is 120. So I'm trying to show, it's hard to draw, but this is a planar part of the molecule. This F and these 2 lone pairs are making a plane, like a trigonal planar, okay? And then these F's here. So that's what we have here. And this is, again, equivalent to that. So this Lewis dot diagram is equivalent to this. Both of these are correct, okay? But I think that this really helps you think about the shape here. Okay, show formal charges. All right, well, the formal charges should be easy to do. And remember, it's going to be the valence electron. So if we go to the fluorine, I don't care where you do it, but each fluorine is going to be the same. They have 7 valence electrons. That's the electrons you bring into the structure, okay, minus the assigned. That's all the lone pairs, 1, 2, 3, 4, 5, 6, and half the bondings. Okay, so that would be 6. And so, I'm sorry, 1, 2, 3, 4, 5, 6, 7. So that would be 7. All right, so again, we brought in 7 valence electrons, and we're going to use 7. And of course, that's going to be 0. And that makes sense. The reason why I caught my error is that I know that fluorine likes to make 1 bond because it needs 1 more electron to be shared to fill its 8. So it brought 7 to the table, and it's using 7. It's using its lone pairs. Remember, it's the valence electrons minus the assigned electrons. The assigned electrons are half the bonding and all of the lone pairs it has. And that'll equal 7. So in any case, all of the fluorines will equal 0. Okay, lone pairs don't get that because there's no bond. And then, of course, what's the iodine? All right, well, the iodine, we'll write that as black. Okay, the iodine also is a halogen. Okay, so it has 7 valence electrons it brings to the table, minus this, of course, the assigned electrons, the electrons it's using. Okay, now it's using half of the bonding ones, so it's using this one, 1, 2, 3. Then you count the lone pairs, 4, 5, 6, 7. So that's another one, 7 minus 7, and it's 0. And so we get a 0 on the iodine, and we get zeros all across the board for the fluorine. And that makes sense because the entire structure does not have a charge, okay? And it's the most stable structure. There's no other real structure to draw here. All right, so in any case, we have a Lewis dot diagram. We've shown the formal charges in our calculations and are ready to move on. So what's electron domain geometry? What's the geometry of just where the electrons are around the central atom? So iodine has 1, 2, 3, 4, 5 pairs of electrons surrounding the central atom. And as I already mentioned, it's trigonal bipyramidal. Remember, the way to think about this, it's a top of a three-sided pyramid. Okay, so you've got the top and you've got this pyramid that comes out, and guess what? It does the same thing on the bottom. So you've got the pyramid it's planar, and you've got the top on both sides. All right, so this is a trigonal. If you only had one side in the sp3 family, okay, for the molecular geometry, if there was one lone pair, it's trigonal pyramidal. But we call this trigonal or triangle. We say bipyramidal because it's on both sides. This fluorine is what's on the bottom, and this other fluorine's on top. So trigonal bipyramidal or bipyramidal. Okay, and again, it's a mouthful to say, and it's kind of makes you feel smart, but trigonal bipyramidal, the shape makes sense. Okay, the molecular geometry. This is where the atoms are. Okay, so where are the atoms? Okay, well, the atoms, of course, all right, are everywhere except the lone pairs are. So we have a couple of lone pairs here. So we can't consider trigonal bipyramidal because we don't have the atoms here. If they were here, it'd be the same. So what is this shape? Well, lone pairs are on the axial position, and you can probably see this with two lone pairs in the, the lone pairs are in the equator position. This is the axial. So in the sp3d family, these lone pairs in the equator positions, this leaves us with a T-shape. And that's what this is. So this is T-shaped. Okay, bond angles, and it's approximate. Okay, and so what we know about the trigonal bipyramidal, there's 120 bond angles in the equator position. But because of these lone pairs, there's not a bond here. So what you have left, if you can see this, is that these would be actually 90. Right? The T shape is 90. So you could say 90, and from F to F, 180. So really there's two answers here. There's 180 degrees, and that's between the what? The fluorine and the other fluorine on one side. And then, of course, there's going to be 90 degrees between the fluorine and fluorine on the other side. Okay? And so you really needed two answers there to answer that correctly. All right, moving on. Is it a polar molecule? Okay, well, one way to think about polar molecule is, and again, we have to think three-dimensionally, do the individual dipole moments cancel? Is this a very symmetrical question? Well, we know the fluorines are all the same, so the bond energies are all the same, the bond dipoles are all the same size, but will they cancel? Okay, and if you think, even the way that I drew it, okay, and if I was to draw these, and I'm going to do this, I have fluorine that's pulling charge away from the middle iodine. I have another fluorine that's 180 degrees. What? I can't draw, but you get the idea. That'd be going straight up, and this other one is pulling outward 90 degrees. So knowing your bond angles, you can guess, assuming this is going straight up, and they're the same size. And why are they pointing to the fluorines? Because they're more electronegative. We could see that the top dipole would cancel the bottom, but we wouldn't cancel the one going out. So we're going to have an overall dipole moment, okay, going this way. And I really should show that. I really should, because on your test I'm going to ask you to. So my dipole moment's point, overall molecular dipole moment goes this way, and my partial negative is here, and my partial positive, believe it or not, is right here. Okay? And that's something I probably should have drawn already. Feel bad. But now I'm over it. Is it a polar molecule? Yes. Why? Because there's an asymmetrical distribution of electrons. There's a what? An overall dipole moment. The bond dipoles do not completely cancel. Okay? All things we should have learned already. Okay. Number of sigma bonds. Well, number of sigma bonds means how many single bonds? We all have sigma bonds here. single bonds. Okay, second and third would have a pi. All right, so sigma bond is a direct overlap bond between orbitals. Okay, and so between this I and F, we have an sp3d orbital overlapping and unhybridized. So we got 1, 2, 3 sigma bonds. There's only 3 single bonds here, 3 sigma bonds. Okay, any pi bonds? 0. No, there's 0. There's none because there's no second or third bond, which by the way would require an unhybridized p orbital. Resonance? The answer is no. And why isn't there any resonance? There's no resonance here because, all right, I don't have a single double scenario. I don't have formal charges telling me I could add a double bond somewhere, somehow in one of these. And if I was to have a double bond in one place and single bonds in the other, that double bond in a pi bond could delocalize to other positions, but that's not happening here. By the formal charges, this is the best structure with single bonds, so therefore there isn't any what? Pi bonding electrons that can move to other positions. Okay, so that would be that'd be a no. All right, and then we're going to draw it. Okay, and so how in the heck do I draw this? All right, well, you start with how many orbitals you have. All right, and I'm going to give myself some space here. So I know it's sp3d, there's 5, and I know the shape, so I know I'll do my best. Okay, it's tough to draw, but here we go. We have 1 sp3d. All right, and then we're going to have another sp3d. We're going to have one that comes out. That's one of my equators. And then I'm going to have what? This is my 120 bond angles. I'm going to put the 2 lone pairs here. Okay. And then I'm going to draw my fluorines. Okay. I probably could have drawn that a little better. So I'm going to erase that best that I can. And I'm going to redraw that. I think that makes sense if it came out better. So these are all sp3d. So the black orbitals are sp3d, and there has to be 5 of them. There's 1 s, 3 p's, and 1 d that mixed. 5 orbitals go in, 5 orbitals come out. Now, it's important to realize that there was 1 electron each. Okay, there's a total of 7. And then the fluorines, because they're terminal, they don't need to have hybridization. So what they just have is a what? An unhybridized p orbital that needs to be filled, and there it's px, py, pz. I'm going to draw the s a little smaller so we can see the overlapping. Okay, and put the valence electrons in. It has 1, 2, 3, 4, 5, 6, and 7. Don't forget that this orbital is filled. All right, I'm going to draw that another time, one more time here. I'm just going to go fast now. The unhybridized p one way, unhybridized p in the other. Coming at you. Draw the s. Put in the valence electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I feel like I'm missing electrons. 1, 2, 3. And there's a 6. Oh, yeah. And of course, 7. Okay, and then another one down here. Ooh, whoop. There's my noise. And draw my S, unhybridized. There's 1, 2, 3, 4, 5, 6, and 7. Okay, and there it is in all of its glory, sp3d, and there's 5 of those, right? Right there. I'd write them in there if I could, but it's too small. And there it is. All right, let's move on to the next one. Okay, so NO2 minus, this is a polyatomic ion. This is a cluster that sticks together. It's going to make ionic bonding. This is the nitrite ion. Any case, it being negative tells me add an electron to my diagram. So I'm going to start with N. I know it has 5 valence electrons, so I have a tendency to just write it like 1, 2, 3, 4, and 5. Okay, now I know I'm going to add an electron here. Okay, well, it's 1, 2, 3, 4, 5, and I added 1 to make 6. Okay, so now I'm going to add oxygen. And I'm going to put oxygen here, and I'm going to put 1, 2, 3, 4, 5, and 6. Now, I don't know if this is right yet, okay? But I'm just going to throw them out there, making one bond. I don't care that right now the nitrogen's given 2 to the oxygen. It doesn't matter to me. I'm just putting out the electrons, and I'm keeping oxygens together. Okay. Now, something I know about this is that unlike iodine, nitrogen, the central atom here, is a row 2 element. It is locked by the octet rule. N equals 2 by the Schrodinger equation. The quantum numbers of L is 0, L is 1. Only 8 electrons can exist here. Now, right now, the way that I have it written, nitrogen feels only what? 6. So what I'm going to do here is make a double bond. Okay? So again, you could have done this on the other side, but I'm going to put the second one here. All right. Now you say, okay, great. Now, how do I know to stop there? Well, I know that nitrogen, okay, nitrogen must have 8. And by sharing with this double bond here, it feels like it has 8. And of course, this oxygen feels like it has 8. All right. Now, you may say, well, Mr. Grotsky, I know that, how do I know not to add another double bond here? Because I know we've done structures. Well, what's the formal charge here? Formal charge of oxygen with the double bond is 0, right? It has 6 valence electrons minus what's assigned. Half its bonding, 2, plus its lone pairs, 6. So this is 0. Oxygen loves to become 0. This half its bonding would be, and so it's half its bonding. So you'd have to add this black electron, and of course add the 6. So 6 minus 7, this would be -1. And then what would be nitrogen? Nitrogen would be half its bonding here, so you would include these blue ones. So 1, 2, 3, 4, you add its lone pairs, and then half its bonding here, 5. And that would give you 5 valence electrons minus 5. That'd be 0. So the -1, which we have to have because we added electron from the environment somewhere, is on the more electronegative atom. So this is the best structure. Okay, so this is clearly the best structure. I can't add another oxygen. Okay, because you may say, well, I know oxygen likes to become 0, but I can't do that because if I add a double bond here, this would become now 10 electrons, and I'm locked by 8. So I'm stuck like this. Now, if you notice something, I'm going to clean this up. I'm going to clean this up to make some sense to myself. Here's nitrogen. Okay, it's got a lone pair. It's got a bond, a single bond with my oxygen. This oxygen has, of course, 1, 2, 3, 4, 5, 6, as 6 total lone pairs. You're going to make sure that you always draw your lone pairs. This is a double bond to an O. And this has, well, 2 less lone pairs. That's important. And I know this is the best structure based on formal charges that I just showed here. But wait a minute. This middle N is what hybridization? How many regions of electrons do I have? I have to include the what? I've got to include the lone pair here. So 1, 2, 3. I don't count the pi bonding. Okay, 1, 2, 3. So there are, for hybridization, 3 domains. And therefore, an S and a P, 2 P's came together. And it's sp2. And the thing here is that 1p is not hybridized. So that 1p is coming right at you, which means if I have a double bond between an unhybridized p here with the terminal oxygen who is unhybridized here, that electron is able to do what? Move over here too. Yes, we have resonance. And if you don't like that, think of the idea that, wait, if I got a double bond on one side and a single on the other, couldn't it also be on the other side? So what we need to do is draw a second resonance structure. And if you do not, this is wrong. So N has a lone pair here. I'm going to show a double bond over here. I guess I'll stay color coordinated. Now with a double bond, there's only going to be 2 lone pairs. Then a single bond over here with another O. all right, O'Reilly, and then that's going to have, of course, 3 lone pairs. And of course, because we have added an electron to this system, I should be showing brackets and a charge of -1. If you don't have the brackets, I'm not going to take away, but if you don't write -1 next to your structure, that's also a deduction. But I needed to draw 2 of them. This is showing resonance. Why? There's delocalization. Why? This central nitrogen has an unhybridized P that's bonding with this unhybridized P. This oxygen has an unhybridized P2. So these electrons are free to move throughout the entire what? Molecule. Therefore, when I ask you about bond order, what would the bond order be? I'm not asking here, but if I was, how many bonds do I have? 3 total bonds. How many places can I have bonds? 2. The bond order is 1.5, screaming to you that the energy to break the bond is bigger than a single bond, okay, but less than a double bond. Okay, it's something in between because of this blending. Remember, resonance isn't flipping of these two, it's the blending of the two. So real quick, it's sp2 hybridized. I can see the shape already. And this is going to be the electron domain geometry, the geometry of where the what? Electrons are. Okay, this is going to be trigonal planar. Trigonal, I can do this. Planar. It's a triangle on the same plane. Okay, molecular geometry, where the atoms are. Bent. That lone pair bends it downward. We don't count that lone pair. It's important for the shape. If it wasn't going to be there, it'd be linear. Approximate bond angles for sp2. Hey, these are 120, a third of a circle. Okay, we've been down this road before. Polar molecule, not applicable. This is ionic. Asking whether something is polar or nonpolar if something is ionic is like asking the marital status of the number 5. It makes no sense. You put yes, it's a deduction. Number of sigma bonds. There is 2. The first bonding overlapping occurs. Okay. Number of pi bonds. I know it has resonance, but in one of the structures we'll look at it and we'll say 1. Now, if you did say 2 because they blend over, I would accept it if you had this resonant structure, but I'm looking at just 1 here. I know it blends back and forth, so if you did say 2, I would accept it if you have resonant structures drawn. Not a real clear-cut answer, but in this diagram you do have 1 drawn with your dots. Resonance, yes, we've been down that road, and now we're going to draw this. Okay, so we've got sp what? Start with the hybridization. I'm going to move this down. So sp hybridization, here's my going to be place where my lone pair is. And then a 120 bond angle of another sp2. That's going to have 1. And another one with an sp2. And we have, let's do the oxygen, which is unhybridized. Okay, and this is going to be challenging, but we'll do the best we can here. Here's an unhybridized P. Here's another unhybridized P. Another one that comes in and out. This is the one that comes in and out. Boy, tough to draw. I get it. All right. And we know we have 6. We have 1, 2, 3. Okay. 4, 5, and 6. If you notice something, I have 1 unhybridized P. Okay, that's not satisfied. This one's satisfied because I put 2 in this one. This one's satisfied. Okay, now let's draw the other single bond on the other side. Oxygen, we have our what? We have our P. Yeah, that one's better. And it's harder to do it in the computer for sure. And then, of course, same idea here. I'm going to have 1, 2, 3, 4, 5, and we'll do 6. Okay, there's my sigma. Where's my pi? Well, party people, don't forget, there's an unhybridized p. If this is sp2 here for all these three, that means I have a what? Unhybridized p coming out and into the board, okay? And so that's on the same plane as this one. Okay, very hard for me to draw this, but what's going to happen is we're going to put, because it's open, this electron can fly here and then fly here. That's the resonance. And then this electron can fly through this one and then fly through this one. And that's where you get that mixing. So that's where that blending comes in. I know it's hard to draw. I did my best there, but I hope all that helped. Okay? Good luck.